Hi everybody. Oh wow, is that what I look like? Good grief. Maybe I should go to a lower resolution camera when I'm doing the face shots here. I don't know. Anyway, welcome back to my first attempt at an official video with the new setup here. And what we're going to do is we're going to start the restoration of the, let's see if we can see it here, the CA-2000. And this is the old one that had the rusty covers and all that good stuff. I sent the covers off to New Image Powder Coating, and they actually thought they had that color, that kind of bronze color, in stock, and that they're not going to have to color match or do anything like that. They're going to just have one that's going to be very close. So we'll see how it turns out on this one. If it turns out good, then these other two over here, I'll go ahead and send the covers out to them and have them done as well. I thought maybe it would be interesting today, and this is mainly an exercise for me getting used to this thing. I know I'm going to screw stuff up. I know I'm going to forget to switch things and turn things on and off and whatever, but so bear with me as I get adjusted to the new camera system. Hopefully we'll all like it, and it'll be quicker for me to record without having to move cameras around as much, and it'll be more views and things for you to see too. So what we're going to do is let's go over the schematic on this, because I'm really excited to see what it looks like to put a schematic up on the screen and go through it with you. So let me get that set up and then I'll be right back. By the way, I wanted to mention a couple of you viewers, my awesome viewers out there, taught me a few things about this switcher here, this Atom or however you want to pronounce it, Mini Pro. And that is, first of all, remember in the last video where I introduced this setup, I mentioned that certain cameras won't work on ports 2, 3, and 4, but they all seem to work on port 1. Well, there's a reason for that. Apparently, when you plug in port 1, that's kind of the master port, and it kind of sets the pace for the rest of the ports. And it's a lot more forgiving for different kinds of video. But once you plug something into that, the other ones have to follow suit and be the same video. Now, I read that somewhere, but I guess it's a lot more finicky about it than I realized. So even if I set the settings in the camera, there may be some other things, though, that it still doesn't recognize. So I'm still messing around with it, but right now on the camera you're looking at right now is a Panasonic Lumix GH5. And the one that's up above, I'll kind of show you, is the ZV-1 Sony. And we'll just kind of see how that looks. I can give you a quick glimpse. That's kind of what we're going to have, and I can zoom in. The only thing I noticed, so I'll zoom in a little bit, but the only thing I did notice about that is there's just, even the weight of that ZX1, which is my lightest camera, it still bounces a little bit until it settles. So I have to watch I don't bump it, or you're all going to get seasick here pretty quickly. So anyway, let me get the schematic set up and let's see what that looks like. Okay, so here we go. Let me see if I can do this. So the first thing I want to bring to your attention is on the CA-2000. They were touting two new features. So this manual, the service manual with this, does not really have a theory of operation, except for this one page. And there's two things they want to bring to your attention, and that is that they're using the new current mirror circuit. And let me see if I can do picture-in-picture too. I'm interested in, yeah, there it is. So you could see that you have this current mirror circuit up here. And what is a current mirror and what does it matter? Well, long story short, and hold on one second. Let me see if I can zoom in on this. Okay. So if we look on here on the schematic, or on this little block diagram they gave you, they're showing the you know, the polarity of the signal. So if you have a positive going waveform, when it comes out of this side, it's a negative going, it's inverted. You can see. So anyway, R09, you have your plus 35 volts coming in. This is called your tail resistor. This setup is a differential, or called a long tail pair. And R109 is usually a higher value resistor, and it actually acts as a constant current source. Now, the reason you want to do that is you want this to be a voltage amplification, or in this case, it's going to be unity gain. They're not even going to have gain in it at all. And as such, if you feed these directly with a voltage, what can happen is the circuit can kind of breathe, is what I call it. But what happens is, as the amplitude changes across a transistor, it's going to draw more current, and as the current changes, the voltage changes, and between these two, and you get what's called common mode interference, or common mode distortion. Why is it called common mode? It's because it's common to both transistors, and you don't want that. You want these transistors to work against each other. So you're always going to see a difference between the two of them. So whatever the difference is in the bases, you're going to get an equal kind of a difference, on the emitters, or on the collectors. In this case, this is a PNP setup. And so this is for common mode rejection. So it would be, the best way to describe it is the ratio of the common mode signal amplitude as opposed to the differential mode signal amplitude. So the whole idea is you want the common mode signal to be 0 in a perfect world, and therefore, it doesn't influence your differential mode, which is the difference between these two outputs here. So anyway, this circuit has been around forever, and it's been used in amplifiers for a very long time, especially at the front end of an amplifier, because essentially this first transistor just acts, ignore this bottom part for a minute, this part right here acts as like a class A amplifier, and usually when it's at the input like this, it's going to be unity gain. In other words, this amplifier will have no gain. Whatever signal level you put in, that's at the base, that's a signal level you'll get out, in this case at the collector. So, but when you apply a signal into the other transistor, that signal will oppose this signal. So that's how a feedback loop works. And you can see NF loop, negative feedback loop. That's what that stands for. And this resistor up here, this tail resistor, as we said, acts as a current source. And so the change in voltage drop across this resistor, when compared to the change in voltage across the transistor, is going to be relatively low. So for all intents and purposes, this thing acts like a current source. Now, in the never-ending quest for perfection, everybody wants to make their amplifier a little better than the last person. You can replace this resistor with an active current source, which would be one like a transistor and a diode, or a transistor and a LED, or 2 transistors. There's a couple different types of current sources you could put up in here. There's integrated circuits that do that, whatever. And that will reduce the common mode even more, because theoretically this voltage across here will still change, and you will still get a slight change in current through the circuit. It's so tiny that you really don't notice it, but there's those who say they can, so you put the current source. The next problem that you have after that is even though you have one constant current that's divided between the 2 transistors, once they get down here, it's fair game who gets to hog the most current. So if you don't have a perfectly matched set of transistors, then one transistor could actually draw more current than the other, And once again, you could get common mode noise again, or a common mode distortion. So in an effort to fix that, you use very carefully matched transistors so that their VBE and HFE, but mostly VBE, are identical, or as close to identical as you can get. And you also thermally couple them so that any temperature change is going to change both of them at the same rate. And that keeps that to a minimum. But of course, the never-ending quest, huh? You can put what's called a current mirror. And that's what this is right here. So what that's going to do is, let's say these transistors are not perfectly matched. If you change, or if one of these has a little bit different VBE or gain or so forth, or turns on a little harder than this one, what's going to happen is this is acting like a seesaw. It's always going to try to balance out. And what it's going to do is it's going to ensure that there's an equal current flow in each transistor at all times. So this truly becomes only a voltage dependent circuit. So only voltage is the only change that's going to happen, because the current is going to be constant from this current source, this tail resistor, and it's going to be mirrored between the two elements, the two transistors, by the current mirror. So this was an addition, and of course they could say, well, we have the absolute minimum amount of common mode signal that you could possibly have in there, or distortion you could have in there. So this has the highest amount of common mode rejection ratio. And that's the whole purpose of this, and that's what's going on. And we can actually read through some of this, and it'll tell you what the advantages are. And there you go. See there, the CMMR is the ratio of your differential gain to your common mode gain. I think I said it backwards from that, but same idea. And if you want to read this, I mean, feel free to do so. You could stop the video here for a second. The second thing that they were talking about, and here you can read the rest of that. I'll turn the picture off for a second. Then the second innovation, we'll call, that they put in this preamp is the 4-gang volume control. And I'll show you that in the schematic here in a minute. But essentially, what they're doing is they have these two volume pots. And see the little dotted line? It means that they're connected to the same shaft. So when you turn the volume knob, you're turning both of these at the same time. Just like a stereo pot, except there's 4 of these. There's 2 of them that control the left channel and 2 of them control the right channel. And what they're doing is, right where the signal comes into the preamp, you have your first volume control. And that's normally how you do it. But let's say there's a little bit of noise, like from your transistors, a little bit of hiss or background hum or something, tiny amount. But let's say there is some. What's going to happen is, even though this is turned all the way down at the input, you're still going to be hearing that coming through here if you didn't have this second volume control. In theory, that's what they're saying. So by putting a volume pot here, and then you turn both up at the same rate together, you're bringing the input signal to this stage and to this stage up from ground at the same rate. So you're keeping the noise to a minimum. In theory, that's what they're saying. So this particular preamp is going to have a 4-gang volume pot, and I don't think you can see it without removing, while we're talking, let me see if I can pop this little module out, and then you can see what I'm talking about. And I'll move, and again, this is something that they were touting as an innovation. So I'll show you this. Let me get this out of here for now, so you can see it. And I'll move you over to the overhead camera. Hey, how about that? Nice. Okay. And let's see what this thing's stuck on. There we go. So you can see right here, there's 1, 2, 3, 4, 5, 6 elements to this thing. That's your volume control. Crazy, isn't it? And it's a 6-gang volume control. So each stage has its own volume control. And that's how they do that. Imagine if you had to replace this thing. These are very, very, very difficult. If they get noisy, if they get dirty or corroded, they are very difficult to clean. So you really hope that these don't go bad. And I can tell you, if you get one of these preamps and this pot is defective, broken, bad, whatever, somebody sprayed it with stuff they shouldn't spray it with and it ruined the internals on it or something, good luck finding one. The only way you can find one is to harvest it from an old, an older unit. So let's go back to the schematic. And you can see right here, this 2691 boards. There's 2 of them here, left and right channel. And here's your input pair, just from that block diagram. Here's the one for the other channel here. And then here is your current mirror right here, and your tail resistor up here. Let me see if I can zoom in. Okay, here we go. So you can see right in here, there's your input pair. There's your current mirror. Here's your tail resistor up here. And then if you go and look at the volume control, let's see if we can find it in here. There's your first one. You can see for the first channel and the second channel. Then we move over a little bit, and you can see, where's it at? The second volume control, hold on, right here. Okay, and then I believe, I don't know where that third one is, but there's even that third one. So yeah, right there, I believe. That's it right there. So you can see 3 different, and each one is a separate volume, and they're all connected together for that, for each stage. So going back, you can see there's not a whole lot going on here. You have your, you have the phono stage, you have the power supply down here at the bottom. You have this headphone amplifier, which uses this little integrated circuit, and it's a BA312. And believe it or not, that BA312, it looks like an op amp. You see the triangle there, but it's actually not an op amp. It's actually it's a little transistor pack. There's 3 transistors and a couple resistors inside of it. You can build the little circuit yourself if the chip goes bad. You can spend a whole lot of money for a new old stock chip that's getting harder and harder to find. And then there's another company called, I think, Spark Labs, or I'll have to look them up. I'll put them up there. They make a module, but it's not compatible with the CA-2000 right now. They made a Sparko, I think it's called Sparko Labs. And they do make a module, but it doesn't work with this particular unit. Maybe they will one day. So there it is. We're going to go through this and go over, as we restore it, we'll talk about the different components and see how it performs. Okay, so I've put this thing together, and we're going to test it out before we really get into changing anything. So let's just kind of see where we are. And this is a preamp. They don't draw heavy, high current. They're not as critical when you're powering them up to worry about current and so forth as a big power amplifier would be. But just to start getting into the habit, I'm going to go over the process that I use for powering something up that's an unknown. And this is going to work for this, but it's also going to work for big power amps and so forth. Now power amps, they're special. There are special cases where if you have something like a Carver amplifier that has one of those triac magnetic field power supplies, or certain types of vacuum tube equipment, certain amplifiers, you really can't power them up the way I'm going to do on this. But general rule of thumb, most basic class A, B push-pull amps and class A amps, preamps, radios, things like that, we're going to be able to power them up this way. So I always start out, let me move the keyboard, by looking at the input where the mains is. You can see up here, first thing I always check is the fuse. If something is weird, you know, if it's the wrong fuse, if it's a blown fuse, right there's a red flag that you should, you know, proceed with extreme caution. You can see this is at, and this is a multi-voltage system, so that means it'll run on, you know, mains for, you know, the United States, for Europe, for Japan. So it'll run anywhere from 100 volt mains to 240 volt mains. So for 100 and 120 volt mains, they want a 2 amp fuse, and you can see that's exactly what's in here is a 2 amp fuse. So we'll put that back in. I always check that first. And of course you'll catch me not checking it first on another video and you'll call me out on it, but that's okay. Call me out on it because I need to be reminded sometimes. I will say that we should check that. Now if you look here, this is a multi-voltage system. So this one is already configured properly for where I live over here in the United States. It's 120 volts. If you were, and to change the input voltage, you just remove this jumper, line the arrow up with the voltage of your mains that you have, and then plug it back in. And you see, like that, or for Japan. So it's simple as that. I love these setups like this because it's really easy to change the mains voltage on them. So it's set properly. Always check that, because let's say you purchase this thing online and you don't know where it came from, and it's configured for Japanese power for 100 volts mains, and you just happen to live over in Europe and you have 240 volt mains. What do you think's going to happen when you plug this thing in? I mean, of course you can look at the type of plug that's on the end, and that can give you a clue as what mains it should be connected, but don't always go by that. These can be changed. You see how easy it is to do. People do that. Okay, so we know we have a good fuse. It's the correct value, and it's set to the correct mains voltage. The next thing I'm going to do is I look at the fuses down here. Let's see if I can zoom you in. Wow, we can get in pretty good on this. Okay, I'm going to like this. All right, here's our fuses. And if we look once again, they all appear to be good. And we can just as easily zoom back out. And we'll check our fuses. All right. That one seems to be good. That one's good. And that one's good. And remember, this is a 1/2 amp fuse. 1/2 amp fuses have really thin filaments, so you can see that it's a little over 1 ohm, including the lead resistance. So that's normal. Okay. Another funny side story. One of the engineers I worked with worked in a company. He worked actually for Toshiba and was a bench tech for them. And they were working on boards, and they got a new trainee in who came up to my friend and said, "Hey, I think I found the problem." And, you know, of course, my buddy Andy, he's kind of a character to begin with, and he says, "Really? What'd you find?" And "This fuse is shorted." "Oh," he said, "it's shorted. It's a shorted fuse." "Yeah, it's shorted." "Well, you better go put another one in there." So, of course, the new tech goes and grabs a fuse, and this one's shorted too. So he went through about 2 or 3 fuses before, yeah, he got really mad at my friend. But hey, that's how you learn. Yes, he strung him along a little bit, but that's a lesson that person will never forget. So anyway, we have good fuses. I don't see anything out of the ordinary on the power supply. I don't see any swollen capacitors. I don't see any burn marks. I think it's safe to try to power this up. Okay, I have you zoomed into the bulb tester. And again, you can just use a simple, light bulb socket. And, I've shown many times how to make a simple one out of an old extension cord and a lamp socket. It's very easy to build. So we're going to plug this in. I'm going to make sure the power switch is turned off on the amplifier. And I'm going to make sure this thing's set to limit so that it's going to use the bulbs. And since this is such a small stereo, because it's not an amplifier, it's a preamp, it's very low current, I'm only going to use like a 40-watt bulb here. All right. So I'm going to turn this on. And you can hear the big transformer back there buzzing. And what I'm going to do is I'm going to power this thing up, and we're going to watch this bulb. And as these two capacitors charge up, let me kick you on to picture-in-picture. So as the two capacitors charge up, these main filters, what should happen is this light should flash on, and then it should dim back down to almost nothing. So let's see what it does. That was pretty uneventful, wasn't it? Hope you caught that up in the corner, because that was very quick. So now this thing's powered up, and we can go ahead now and check some power supplies. And I have to zoom you out a little bit. Okay, so here we go. And your AC is coming in on this side, and all your DC supplies are out here. And we can look at the schematic, but you can pretty much tell your positive and negative supplies by the colors of the wires and the locations and so forth. So the black wire is most likely going to be your ground. So we're going to start out by looking at that. So we'll put one probe on the ground, and then we'll touch one of these blue wires, and notice, you can see the trace in there. So they're all tied together. So this is going to be a negative supply, is the blue one. That's what I'm going to guess. And you can see you have negative 1.6 volts. It's very low. And on the positive side, positive 1.5 volts. So you have a very low voltage. And that could possibly be because we don't have, well, let's check from blue to red. 3 volts, okay. So it could possibly be that bulb that's in there because it's such a low value. But being that it's not lit up, it shouldn't have that much influence on this circuit. So we may have to look and see why we only have 1 or 2 volts in there. That's pretty low. We might want to go back and look at the output of the rectifier. So these funny looking discs are your rectifiers. We obviously don't have a short, because if there was a dead short, that light bulb would be lit up very bright, and it's not. So kick you over there. See, it's not very bright at all. Okay. I'll leave that up there in case something goes wrong. Now there's another fuse in here, and we can't really get to it very well because it's all covered in plastic. But you can see it right there. It's kind of standing up, and it's a pigtail mounts one. But let's go and see if we can see something at the output of these diodes. And of course you can't, because they have they happen to have okay, they have insulators on them, so you can't get there. So we may have to look at our schematic to find some good places to check our voltages. All right, looking at our schematic, the red wires were all connected to pins 10 through 13, I think it said. like right at 10 through 14, and it should be plus 32 volts. And then the blue wire is 15 through 19, it should be minus 33 volts. And we're not getting that at all. And, you know, with reference to point J, which we were on, or one of our 0 volts. The other thing is we have a plus 50 volts that is in the way right now. There we go. Right here we have plus 50 volts. So let's see if we have that. And I will go back to my overhead. And from here to this orange wire, 51 volts. Do you see that? So we're good there. So it seems as if we are missing our plus and minus 33 or 32 volts, whatever you want to call it. So this whole center section here, let me go back. This whole center section is not working. So we need to find out why. Okay, I think perhaps we have come across another Sansuiism. I just coined a phrase. So if you look on this schematic, you only have these 3 fuses on the board, and which is, you know, F1, F2, and F3. But there's a 4th fuse that we have on this one, and it's this one right here. You can kind of see it down there. And if I try to measure to that, I have nothing on that fuse at all. And I don't even know where it goes, because that appears to be an add-on that they put in there after the fact. Sansui is a big one to modify their circuitry mid-production run and not always do the best job of documenting it. There will eventually be a document out, released, but Sansui is really good for that. I've noticed that. Any of you watched my series on the 9090 that I did? There was a lot of that going on in there. I kind of went over it and explained it to all of you. But anyway, this fuse may possibly be open. The problem is it's not in the schematic, so we're going to have to figure out where it goes. So we're going to have to flip it over to see where it goes. So I'm going to leave this on. I'm going to just kind of turn this over. And it does not appear as if any work has been done on it. The fuse is back here. So somewhere along in here, I'm hoping we should be able to see our fuse. So ground should be, I believe this was ground, if I'm not mistaken. Yes. So if I go over to, there's 2.1 there, 51 volts there. And I think, see, there's 53 across that. That is where I think the fuse is that we're missing, possibly. So I think we have an open fuse. So let's remove it and let's see what we have. Okay, let's see if we can get this thing out without too much trouble. That appears to be it. And then I think this is the other part. And it would help if I loaded this thing first. Okay, so let's see if this will come out, and then we can measure it. Oh, okay, I took the wrong component out. I'm leaving it in there, don't worry. Got to have somebody to have a chuckle with me on this, huh? here if I can make a mess of things. Yeah. And there's a part of this trace is munched up. Part of that could be me. I could have done that. Okay. How about we put that resistor back in? So we don't need that to be floating around and falling out. Now, if this was a great big amplifier with great big capacitors, I would make sure that they are properly discharged. Okay, so I'm going to pull that one out. And then the wire right next to this one is still sticking. Okay. There. Of course, I'm going through all of this, and probably the fuse will be good. But there's only one way to find out. And sometimes there's things in circuit. It's a good fuse. At least it acts like it is. Yep, good fuse. So that was futility, wasn't it? Well, good. You got to see what is not the problem. See, I meant to do this so that you could all see that this is not the problem. This is what it looks like when it's not the problem. How's that? Some of you get all uptight about that stuff. Other of you laugh along with me on it. But hey, you got to lighten up. You're going to be on this channel with me. I have fun. I don't worry about things. Not a big deal. All right, put you back in. Let's just mess up all of this on camera and knock the keyboard over. It's all good stuff. And you know what? I'm going to give that a little more, that trace a little more area to bite onto. Where's my little baby screwdriver? Here it is. Because that trace is kind of small. So I think the other thing you're going to get to see a lot with this new camera is my top of my head when I'm working on stuff like this. When Mr. Magoo's trying to see something. There we go. There we go. Much better. How about that? And I probably should use the smoke extractor, but I'm just being lazy. So we're now going to need to use the schematic and try to go through why this thing is not powering up and find out why we're not getting our plus and minus. Okay, back to the schematic. If we look at the input here to that regulated supply, we should have plus and minus 54 volts. And we can read that very conveniently across these two big capacitors, which just so happen to be right down here. So we're going to go ahead and measure those. Let me see here where we are. Yeah, they're over here. So let's see if we can measure a voltage across them. Now, if I wanted to get all fancy with my cameras, I probably could go ahead and put one of the cameras on one of the bench meters and let you read it that way. But hey, I'm not going to give you all that. I mean, you know, some things I'm going to do the old way just because I want to. If I don't want to, then I'll do it different. But, you know. So let's go on negative here. Let's look here. Oh, it helped to go on volts instead of millivolts. Okay, so there's your minus, and there is your plus. So we do have an input, and I suspected you would. All right, so now let's go back up here, and let's look at TR606 and 605 and see if we have anything on those. I'll have to find that first on the schematic. Okay, where it makes sense, I'm still going to use paper because I like using paper. I don't like staring at a computer screen reading a schematic. It's just me. It's a personal thing. I'm not saying it's wrong to read a schematic on a computer. I'm just saying it's the way I like it. So looking here, it's oriented this way. I got it the right way. We want to look at up here TR610 and TR605, and that would be 605 is right here, and where's, oh, 605 and 606, my bad. So 605 and 606 is these two heat sinks right here, and that would be these right here, and the base is going to be on this side on this one and on this side on this one. So let's go to ground. We want to look at the bases on these. So we're going to look at the base voltage. You got 2.1 volts there. Base voltage there, negative 2.1. And then if we go to the emitter, there it is. And then the collector is probably going to have nothing. So that's crazy. Because if we have looking at this 54 volts here, but we don't read it here, then it tells me we need to check, what is this, R611, and same thing on this side, R608, because we're not getting any voltage going into these two transistors, and the only thing preventing the collectors from having voltage on them is these resistors. So let's see if those resistors are opened up. Okay, according to our diagram here, R611 is a power resistor, and it goes from here to here. It's right in between these two capacitors, straight down from this transistor right here. So that would be this to here and here, right? So let's see what we have. Wide open. Open. That's not good. And then what did I say, 60, it appears to say 608 on the schematic. So R608 is right here. So that would be this one. Go from here to here. Open. Open. So we have two open resistors, and that's not good, because usually when there's an open resistor, it's because something is shorted. So, and it looks as if the camera shut off. Turn back on. Okay. So it looks as if the battery exhausted. So it's overheated right now, and it needs to charge a little bit. So that's another problem with this thing, is the battery dies, because this has a USB charging, but it does not have a external power supply connector on it, I don't think. So yeah, we'll have to play that by ear. Okay, so let's move in the other camera and we will look at it. Right here, like so. And I will zoom out. Look at that. Okay, we're getting some glare, but we're just gonna have to live with it. So let's look at this resistor under here. Okay, so here's our two little resistors here and here. And actually, I'll give you a chopstick. So there's one right here and one right here. Those are it. And they're bad. So we're going to have to replace them, and they are, according to the schematic, they're 120 ohm resistors, but we're going to have to find out why they opened up. Obviously, if they're open, it means that a transistor is shorted, so we probably should check those transistors as well. Okay, so we have the base, and this is, I don't even know if it's PNP or NPN on this side. The base, so let's go this way. Okay, so that's a good one. This one's the PNP. So those transistors are not shorted, so could be something else in there, but to blow that transistor out, or both those out, there has to be something that is drawing heavy current. So not sure what that would be, but there's a whole bunch of things connected in there. And if we go to those two power buses, if I measure from ground to either one of them, just statically, I don't see a short there. I don't see a short there. I don't see a short there. So there's no shorts. So, but for some reason, those resistors opened up. Okay, it's another day, and I'm finding out that every time you turn the EDM back on, all the volume control, the gain settings, everything reverts back to default. And what that does is the microphone has too much gain, and then it drives it into clipping. It's really annoying. The one thing I'm learning about this is you have to do you can't just come down here, turn everything on, and start recording. You have to go through every little setting and make sure they're right. Make sure all the cameras have their orientations in the right direction. And it's a pain in the butt. So I will use this sometimes, but I think sometimes I'm going to simplify it a little bit because, again, I'm here to show you how to work on this stuff and to enjoy my hobby of servicing this. Amateur photography and videography is not my thing. It's to me, it's a necessary evil. For others, it's a hobby that they enjoy, and it is interesting, but I'd rather do this. Anyway, enough of my morning rant. I guess I need more coffee, huh? Okay, so let's remove these resistors. I mean, yesterday we tested, and there really didn't seem to, at least those transistors didn't appear to be shorted out. So the only thing I can figure is that I don't know, at some point in time something overloaded and caused those two resistors to go. I don't know. So let's see if I can get these out of here. Oh, nice. I took the wrong ones out. It's going to be one of those days. Okay, let's take two. I'm not going to turn the air handler on here because it's too loud. I don't really want to listen to it this morning. Okay, these larger pins are the ones I want to remove. I don't know why I did that, but hey, that's more like it. And this is, again, those really flimsy circuit boards. They're not solid. You have to be very careful soldering on them because they will very easily lift the traces. Okay, so here's our resistors. Let's take a look at them for a minute. Let me get this out of the way, see if it'll focus for us. So there they are. They look, this one definitely looks, well, they both appear to be discolored a little bit in the center. Let's measure them once again. And for those of you who are going to give me there's spatial correction errors and this and that in my video, you'll have to live with it. And I know that'll drive some of you crazy. Yeah, see, that one's bad. This one's bad. But again, I can only do so much, you know. All right. You know, zooming in and out when I shouldn't or should or whatever. Hey. Okay, so these are supposed to be, according to this, 120 ohms. So you have brown, red, and brown. So let's see if I can find a 120 ohm resistor. Okay, according to this, R611 and R608 are 120 ohm, 1 watt. And as it turns out, I have a couple of 120 ohm, 1 watt. They look physically a little bit smaller, but they are 1 watt resistors. And again, you don't want to go bigger. It's tempting to put a larger resistor in there, but that is what protects these things, you know, from overload. If something shorts out or draws excessive current, the whole idea is those resistors are supposed to go away. You shouldn't be dissipating 1 watt across that resistor in a normal situation. So let's take these little ceramic sleeves off of here, put them on the new resistors, and let's check our ohmage here. And yes, I have the overhead camera off because I don't want it to die real quick. I do have a battery eliminator on order for it. I'll put it in there. All right, they're good. Okay, this is just going to be the everything video, I think. We'll even do some solder and chat and everything while we're at it. Again, I want to give this thing a good test. So, for some of you who just like watching mind-numbing things, you're going to love this video. Some of you who are just, give me the answer, tell me how the book ends, you know. I don't want to read the book. Yeah, you'll have to skip ahead a little bit. And that's okay too. I do that sometimes. You know, some videos I love watching every last second of it. Other ones, you know, I'll skip along a little bit, especially on busy days when I just don't have the time to watch a whole video. I'll do that. So there we go. And these aren't going to behave themselves because gravity. So I'll give put a little hook on that. Okay. And then we'll put this one in. And Sansui was nice enough to put a little ring. I don't know if you can see it, but they put a little ring shape. I don't know if it'll show it there. You can see right down there, right next to this bridge rectifier, you can see they put a little ring on one of the holes. And that's where the ceramic standoff is supposed to go, and that's the direction that the resistor is supposed to face, which I think is pretty cool. I bet you with all these cameras, I'm still going to go off frame. What can I say? I'm having fun while the back of my basement is drying out with all these machines that they came and brought in to get rid of the water damage. It's total loss. Have to have a whole new bathroom built down there. But you know, these things happen. One of my employees had a foundation problem, you know, and it was a major repair he had to have done. So I count my blessings. I don't complain. That's the worst that happens to me and to my family. No problem. I think we often have a little adversity in our lives and then we lose our minds over it and forget that it could be a lot worse. And it is a lot worse for some people out there, you know. I always try to think of that. When you work in the healthcare industry, you do get to experience a lot of different people and a lot of different situations. You kind of learn to appreciate what you have in life. And you know, your health when you do have it. And even when you don't have good health, if you have the ability to do anything at all, just spend time watching videos or playing around with a home hobby like this, hey, it's, you know what, it's a good thing. Count your blessings. At least that's the way I look at it. We don't all look at things like that, but okay. It appears as though we have replaced the resistors. So let's see now, before we do anything else, I'm just going to power this up. Again, I'm going to hook it up to that really small current limiting light bulb and just see if, let's put some of these tools away. Always experimenting with the bench, you know. It's a good thing to do. This is actually a refrigerator container, and it holds 6 12-ounce cans. So you can put a 6-pack of beer or soft drink or whatever in there, and it holds it in your refrigerator. And I saw that, and I said, that shape is perfect for my bench. It will fit. Instead of the tools laying there all over the bench, they kind of pile in there. These are my most used tools. And then the other ones, you know, I have the drawer that I can store them in. It works out pretty good. All right, turn this on. Had a quick flash of the bulb and it's powered up. And that's a good sign because that bulb is not even, I can't even see it. It's not even lit up. So let's see if we have power now on either side of these. Got 47 on one end and 0 on the other. I think I will shut that off because I bet you that thing is smoking hot. Or no, I did it again. I'm checking across that stupid capacitor again. Why do you guys watch? I know why you watch this. The same reason we watch train wrecks, huh? Okay, there's 48 volts on that side of the resistor and 41 volts on the other. So there's just a tiny little voltage drop there. That's what we want. And on this one, 41 and nada. There, now I'm getting it. 47, 41, 47. Okay, I just had some flux or something I was getting on. So, working as expected. So now here's our your positive and negative rail for your regulated supply. What is it, 32 and 33 volts, positive and negative. There's minus 35, positive 34. Hey, all right. I think we fixed it. So let's turn this back off, flip it around. So you see the process. I mean, I always, and again, this is my personal way of doing things, and maybe it's because of how I do things at work and everything. I always like to start at the power supply and work my way forward from that, because really the power supply can tell you a lot about the rest of the circuit. If a power supply is missing or a voltage is incorrect or something at the power supply, that means something connected to the power supply usually caused that issue. And while you may not know what the problem is, you still at least know that there is a problem. And so what I'll do is check to see if there's shorts or something. Now you can check it statically by just using an ohm meter like I did. Or if you suspect that a power supply is being held down by a short, you can disconnect it. So like this type of circuit is very, very easy to troubleshoot because everything's on connector plugs. So you can actually take, like for instance, here's the red and the blue wire for the phono stage. I can disconnect that, and that will take, if there's a short on here that's holding the power supply down, that would eliminate it and my power supply would come back up. So that's really kind of the method that I use. And I'll eliminate, disconnect the power supply from the different boards until our power supply is correct. If it never is correct after disconnecting all the all the boards, then I know it's isolated to my power supply and I have to repair that. So kind of the way that I handle it. Now another thing, since we had to replace bad blown resistors, I'm going to turn this on again, let it go for a little bit, and I'm going to check and see if these two regulator transistors get hot or get warm. They'll probably get a little bit warm to the touch, but if one of them gets noticeably warmer than the other, then we know that again, one of the power supplies is drawing excessive current. And these are all simple things you can do. Do you notice the only thing I used for all of this, other than the schematics and my mind, is a multimeter? And really, if you were going to buy a piece of test equipment starting out in this hobby, the very first thing you should buy, test equipment wise, we're talking, other than hand tools, is a multimeter. A digital multimeter. I mean, I love the analog meters and all the different things. Those are extras that you can get later. Nothing is more versatile than one of these. In a pinch, you can adapt it to a lot of different uses. And I'm not talking about an expensive fluke meter like this that's $400 or $500. You can buy just an inexpensive digital multimeter. The Aneng, A-N-E-N-G, I think it's spelled. There's a little bit of a story behind the gentleman who founded that company and invented those meters. He wanted to make a very inexpensive, cheap, meter that would perform as well as a more expensive meter, and that could do everything that the expensive meter could do, so that everyone could afford one. And he did that. He pulled it off. A lot of the meters, actually, one of those, the little tiny one that is their most popular meter, and I forget the model number, I actually carry at work. I have a little, call-out bag that I take in. If I'm not doing a big repair, if I just have to check something quickly, I have this little tiny case, so I don't have to bring a cart or anything with my tools in a big toolbox. I could throw that little meter in. It fits in your pocket practically, and it's good enough. I'm not going to check a 480 mains line with it, but if I need to check a 12-volt supply to see if there's voltage there or not, it's perfect. If I need to check continuity, if a wire's open or something, it's perfect. If I need to just check a diode or a transistor quickly in diode mode, perfect. It even has non-contact voltage testing. So, and that's one example, but there's lots and lots of inexpensive meters you can buy. And you can do all of these things just with that. So it's a great tool to have. Now you can get, these are designed to be used every day out in the field, abused, beat up. They're certified so that, for as far as safety is concerned, I have no problem using this meter to check a 480 volt mains line. The probes that come with it, the meter itself, it's designed for it. It's got a reputation. Not just Fluke. There's other big name companies. You know who they are. They're all good. It's all good equipment. So anyway, that's my little schmeal for test equipment. Everything else on this bench, if you took it all away, I could still do a lot of what I do with just this meter. Just keep that in mind. All these other things are fun. They do make things easier if you know how to use a good oscilloscope and signal generators and all these different things. Yes, you can move along much faster because you can test things. You could see waveforms and things that you can't do with the meter, but you can still do a lot with the meter. Don't underestimate this. Okay, let's see if this thing will pass a signal now. Okay, I have a signal connected, and what I'm using is just the cheap signal generator. Let's get the meter, or get the camera on the scope. Hold on a second. Okay, you can see the scope in the upper right hand corner, hopefully. And it's crooked, and yes, I'm not going to mess around with it anymore. You can see what we need to see. Let's turn the signal on. Amplifier, or the preamp, is turned on. And just so you know, I'm using this little splitter box that I made. All it does is it takes the mono signal from your signal generator and it splits it, and then you can apply different load resistors to the two channels depending on what kind of input you're feeding it into to keep the voltage a little more consistent. But anyway, I normally leave it on 1K, but it can do 100 ohm, 1,000, 10,000, and 47,000 ohm. And it just allows you to have a consistent signal to go into two channels when you're checking a stereo amplifier with a mono signal. Anyway, let's turn the thing up and look at that. And one channel is wacky doodle, so let's move a couple switches. Again, that's not doing anything. How about the balance? Well, it really doesn't like that, does it? How about the input? Oh, look at that, I touched the input selector. So let's move this back a little bit. This switch right here, so that needs to be cleaned, but the preamp is working. It's just bad switches. There we go. Don't breathe. All right, volume up, volume down. Looks good. So yeah, badly, controls badly in need of cleaning, but really it looks pretty good. I can put you, I can show you the frontal view. There we go. So there's our signal. Looks pretty clean. Okay, we'll go back to the picture-in-picture. So there we go. We have a working preamp for the most part. So really all that needs to be done is we're going to clean the controls. And what I'm going to do on this one is I'm going to leave everything original for now. We're not going to replace any of the capacitors because, people love recapping everything. I'm not going to recap anything. I'm not going to change anything. I'm not going to touch the transistors, nothing. And then we're going to take the better of the two, the one with the good faceplate and everything, and I'm going to completely restore that one. So anything, all the electrolytic capacitors will be replaced. Any transistors that might possibly be noisy or are known to be high failure items, they will be replaced. I'll go over the whole thing with a fine-tooth comb, and then we will compare the two preamps to see if there is a noticeable difference. Now, we can't audibly check that because you can't hear what I can hear, you know, because everything's going to go through the internet, through YouTube, microphones and everything else. But what we can do is we can measure some things, you know, with test equipment that I have available, and see if we can at least see any testable differences between the two. My guess is that there won't be much difference at all, because these the capacitors on this are probably going to be okay, and these transistors are probably going to be okay. Although the two CA-798s, I have seen quite a few of those get shot noise and so forth. But we'll see. We'll just leave it open. So I'm going to end this video here because it's probably pretty long already, and I want to kind of edit it. I did make some adjustments to my bench, to my camera setup, to the microphone, things like that. And I just want to see how it turns out, and I'm going to post it as it is, and so that I can play it back from YouTube and see for myself what I'm getting with this, and then go from there. Hopefully each video I'll tweak a little bit and get it a little bit better. So until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon with the next part. Take care, everybody. Bye-bye.